Welcome back to another explainer. Today, we're breaking down the absolute fundamentals of how the physical world operates. We are going to look at work, energy, power, and the simple machines we use to manipulate them all. Honestly, whether you're just lifting a pen or building a giant skyscraper, these physics principles are the invisible forces running the show behind the scenes.
But first, I want you to imagine this scenario. You're pushing against a massive, giant boulder. You're sweating, grunting, literally putting in maximum effort, but the boulder doesn't budge an inch. Now, in our everyday language, you're obviously working hard. But in the strict, unforgiving world of physics, you've done absolutely zero work. Nothing. Nada. Why? Well, because effort alone doesn't equal work.
To figure out why that is, here's our roadmap for today's explainer. 1. What is work? 2. Types of work. 3. Energy and transformations. 4. Power. And 5. Simple machines.
Okay, let's dive right into this. Section 1. What actually is work?
Let's go back to that giant boulder for a second. In physics, pushing hard only counts as work if a force actually moves an object in the direction of that force. If you push that unmoving boulder, yeah, you get tired, but no work is done. But if you gently push a small box across a frictionless floor and it moves, congratulations, you've done work. You absolutely need both force and displacement.
This brings us right to our first formula. Work equals force times displacement, or W equals F times S. Both force and displacement are vector quantities, which just means their direction matters. When force and displacement align, we measure the final result in joules, also known as Newton meters.
Moving right along, let's look at Section 2, Types of Work.
Work isn't just a simple yes or no. Think about when a ball falls. Gravity pulls it down and it moves down. The angle there is 0 degrees. Force matches motion perfectly, so we call that positive work. But what if you throw that same ball straight up in the air? Gravity is pulling down, but the ball is moving up. That's a 180-degree difference. That opposing force is doing negative work, exactly like friction on a skidding car tire. And then there's zero work. Say a porter carries a suitcase horizontally on his head. The downward gravitational force is perpendicular to his horizontal motion. That's a 90-degree angle. Mathematically speaking, the work done by gravity here is exactly zero.
So what does this all mean? It literally all comes down to the angle. The angle completely dictates the type of work being done. It totally contrasts with our everyday assumptions, right? You might be carrying a heavy bag horizontally across a long train station and feeling exhausted, but vertically against gravity, you aren't doing any work at all.
All right, let's shift gears to Section 3, Energy and Transformations.
Energy is, simply put, the capacity to do work. If you have energy, you can cause displacement. Think of a bullet. Just sitting there on a table, it can't break a glass door, but fire it from a barrel, give it that immense velocity, and suddenly it has the capacity to do some highly destructive work. Because work and energy are essentially two sides of the same coin, energy is also measured in joules. The work-energy theorem tells us that any work done on an object is exactly equal to its change in energy.
Now, mechanical energy generally comes in two forms. First up is kinetic energy. This is the energy of motion. If you have a speeding vehicle or a running athlete, they possess kinetic energy. The formula is E sub k equals half mv squared. Notice that velocity, the v, is squared. That means if you just double an object's speed, you don't just double its energy. No way, you quadruple it. Velocity dramatically multiplies the energy.
The second form is potential energy. This one isn't about motion, it's about position or shape. Imagine lifting a heavy box high above the ground, against gravity. You are actually storing your work inside that box as gravitational potential energy. The formula here is E sub p equals mass times gravity times height, or mgh. The higher you lift it, the more energy it stores, just waiting to be released. It's exactly like pulling back the string of a bow. Picture a roller coaster for a second. As the cart sits at the very top of a massive hill, its potential energy is basically at 100% and its kinetic energy is 0. As it plunges down, the potential energy drops and the kinetic energy shoots up rapidly as it gains speed. But here's the magic of physics. The total energy combined always remains at exactly 100%. This perfectly illustrates the law of conservation of energy. Energy can neither be created nor destroyed. It only transforms from one form to another.
Let's see how this builds in Section 4, Power. So, what happens when we throw time into the mix? We get power. Imagine two runners at the bottom of a staircase. Both climb to the exact same second floor.
Because they have the same mass and went up the same height, they did the exact same amount of work against gravity. But let's say runner A takes a leisurely 20 seconds, while runner B sprints to the top in just 5 seconds. The work is identical, sure, but runner B finishes way faster, showcasing much higher power.
Power is simply the rate of doing work. It's calculated clearly as work divided by time. Doing the exact same work in a fraction of the time requires significantly more power. It's basically telling us how fast energy is being consumed or transferred.
The standard SI unit for power is the watt. 1 watt is precisely equal to 1 joule of work done per second. When you look at your electricity bill, you'll actually see a commercial unit called the kilowatt hour. To put that into perspective, one of those equals a massive 3.6 million joules. It's just a scaled-up way to measure the huge amounts of energy your home uses over time.
And that brings us to our final stop, Section 5, Simple Machines. Let's look at how human ingenuity manipulates all these physical laws to our advantage. For millennia, humans have used 6 classic simple machines to make physical labor so much easier: the lever, the pulley, the inclined plane, the wheel and axle, the wedge, and the screw. Now, they don't magically erase the total work we have to do, but they profoundly change how we apply our force.
The core concept behind these simple machines is mechanical advantage. It's a real game changer. It's the ratio of the load, the heavy thing you want to move, divided by the effort, the actual force you apply. A machine is truly useful if it gives you a mechanical advantage greater than 1, meaning it allows you to output a heavy load while inputting minimal effort.
Think about an inclined plane, like a ramp used to load a heavy crate into a truck. Lifting the crate straight up takes a massive amount of force over a very short distance, but sliding it up a smooth ramp, that drops the required effort drastically. The catch? You have to push it over a much longer distance. You trade distance to save on force, but the total work done remains absolutely constant.
The lever works on a very similar trick using torque, which is the rotating effect of force. Picture some laborers moving a heavy rock with a long iron bar. The pivot point, or fulcrum, is placed on the ground. To maximize their mechanical advantage, they place that fulcrum as close to the heavy rock as physically possible. This gives them a long, free hand on the bar. A very small effort on the long side creates a massive force on the short side.
So here's the ultimate catch when it comes to physics. Simple machines multiply our force. They let us lift the completely unliftable, but they never, ever reduce the total work required by the universe. Energy is always conserved. We just get to choose how efficiently we apply it. Knowing that every single joule counts and that these invisible laws govern our every move, what will you build with your energy today?